Okay, Unit 3. Integration techniques, L'Hopital's rule, and improper integrals. Starting with some more integration techniques that you did not yet learn from Calc AB. So kind of building on some integration techniques from Calc AB. So far, what kind of integration techniques are you aware of? What have we learned so far? We have like the basic integration rules or formulas. Like the power rule kind of thing, where you bump the power up by 1 and then divide by that power. Stuff like that. U substitution would definitely be on the list. And then separation of variables, even though that's really more of getting it set up to integrate. So as far as integrating, not really all that much that we have as far as different strategies. U substitution is by far the fanciest thing that you're aware of at this point in time, because other than that, it's just like the basic trig rules, just pretty much knowing that the integral of cosine is sine and all that kind of stuff. But let's see what we have in store for us in this lesson. So here's the integral in the first example. Let's evaluate the integral of x cosine of x dx. Long story short, if you tried to just do this straight up, it definitely too complicated to do that. And if you tried to do u substitution, that wouldn't really pan out either. So there's this technique called integration by parts. And that's pretty much what this section is all about. So we have an integration by parts formula. Let's see what this is right here. Is this just kind of like a deeper dive into maybe why it works? We don't really need to go into that in this video. But whenever you have, so this right here would be like your original problem. So if you can kind of somehow match your original problem up with basically the integral of u times dv, like something times, dx, d, whatever, then that can be sort of switched out with this, And again, there is kind of a deeper dive that you could look into about why the integral of some generalized u something, dv, d something, would actually be equal to uv minus the integral of v du. So a new kind of maybe seemingly weird formula for right now, but I think it's pretty easy to get used to. It just starts to kind of roll off your tongue a little bit. The integral of u dv equals uv minus the integral of v du. Say that enough times and it'll start to kind of, like I said, roll off the tongue or kind of naturally fit into your memory bank, hopefully. But so here's what basically happens. We have to take our original integral and figure out, okay, if integration by parts is going to work, what is my u part up here and what is my dv? And I don't know if you want to write this down, but for the most part, a pretty good rule of thumb is that you're going to let u equal something that you want to take the derivative of and have it get simpler. And dv is going to be, the other part. So in this example, we're going to let u equal x, because what happens if you take the derivative of x? Basically just becomes 1, or 1 dx, 1 with respect to x. And if we let u equal x, then dv basically ends up being the rest of it, the cosine of x dx. And that we end up taking the integral of, you know. So we kind of start with what's u and what's dv, but because of what ends up over here in the formula, we're going to need a du, which means we're taking the derivative of whatever we're letting u equal. And we're also going to need a v over here in the formula, which means we basically have to integrate dv. So what's the integral of the cosine of x dx? Technically, we're taking the integral of both sides, and hopefully that's not too tough to think of quickly. And oh, of course I wrote it all out like that. But you're going to end up with the sine of x. So once we have all of this, we can just kind of now like basically kind of just go with this formula, you know, like again, this is the original problem. Once you have everything, you can just kind of write u, v, right? U and v minus the integral of v du. And what you're hoping for is, like, once you've done this, you're hoping that, because you're still going to end up with an integral, but what you're hoping is that this integral is now doable, or at least simpler, like it's on its way to being doable, you know what I mean? And in this case, the integral of sine, we can do that, you know, that's just negative cosine. So that's why, you know, the minus became a plus. And so this one's done. This is the final answer, you know, via integration by parts. So the integral of x cosine x dx is x sine of x plus cosine of x plus c. Okay? Next example. Once again, if you tried to do this with like u substitution, just wouldn't really work out. So let's see if integration by parts will work. And again, this is where you're going to start by figuring out what you're going to let u equal from up here, and therefore, you know, what dv is going to equal. And remember, you're going to let u equal something that you want to take the derivative of, and it'll become like lesser or simpler. And so here in this example, that's going to be x squared, which means dv is going to be e to the x dx. And so du is going to be 2x dx, and v is going to be what? Remember, we're taking the integral to get, well, e to the x. That was easy. And so now we can kind of switch this out with uv minus the integral. Oh, here it is. I wrote it out again. I think just in this example, I kind of like literally wrote out the formula just to, you know, just for the sake of notes and a reminder that that's kind of what we're doing. So u was x squared. There it is. V is e to the x minus the integral of v du. Okay? And I think this next step, I don't know how necessary this next step is, but I think all I really did was bring out a 2. So, you know, cool beans. All right, so now what? See, at this point you were kind of hoping that the integral was doable, you know what I mean? And actually, now that might kind of look nicer. Might be a little too late for you, but that just might be a little more conventional looking, if that makes any sense. Sort of, I mean, close enough to how up here we like to write 2x and not x2. You know what I mean? Anyway, so is this integral now doable? Actually, no. But I hope you notice that it is simpler. See that we started with an integral of x squared e to the x. Now, I mean, it's lesser, it's simpler, which guess what that means we have to do next? Integration by parts again. All right, so now u equals x, dv equals e to the x dx. So now du is just going to be dx, and there's my v. And so now let's just take a second to realize what's happening now. what's happening next, I suppose. So we had this, and then just this integral, just to do this part, we're doing integration by parts. So x squared e to the x minus 2, like that pretty much just gets brought down. And this itself is going to be its own uv minus the integral of v du. So it's like kind of like a nested integration by parts within integration by parts. So this part right here is getting replaced with, from up here, uv minus the integral of v du. uv minus the integral of v du. Yeah. But notice that now this integral is very, very, very doable because it's just e to the x. And along with, distributing the negative 2 and kind of clearing the parentheses, and then, of course, adding the plus c in there, final answer, x squared e to the x minus 2x e to the x, because we're distributing the negative 2. And this minus becomes a plus because we're distributing the negative 2. Doing that integral, final answer. We have an example with an initial condition because, that's a thing. And but at the same time, we have an example involving the natural log of x. So here's something really, really, really big to make a mental note of, maybe even a written note somewhere on in your notes here. But we are going to do integration by parts because, nothing else, I think, would work that you're aware of. And so ready? Again, this is very, very, very important, and that's why we're definitely doing an example like this in our notes. Again, I've said this already a couple times now. I'll say it again. Normally, you would let u equal the thing that you want to take the derivative of to make it simpler. But when there's a natural log involved, that rule of thumb kind of goes out the window. So this natural log example, or like an example with a natural log in it, it's kind of like the exception to that. So we're actually going to let u equal the natural log of x. And we're going to let dv equal x, dx. And look, I just take it at, like, I promise you that this is going to work out, because even though we're going to take the integral of x, instead of the derivative, and basically make it more complicated, make it greater in power, trust me, everything is going to be just fine. Because what's the derivative of the natural log of x? 1 over x. So just like it's going to work out great, trust me. So when we do the uv minus the integral of v du, because this derivative ended up being 1 over x, look at this. Isn't this going to work out like beautifully over here? So just rewriting it, simplifying over here, and what we end up with is actually an integral that's very, very, very doable, Even though we kind of broke our rule of thumb, routine, and ended up with like something greater in power, it all worked out great because of just the way natural log is with its derivative. So what's the derivative of what's the integral of x? X squared over 2, which means we end up with x squared over 4, and then the plus c. And we'd be done, except we also have an initial condition, which we've done a bajillion times. So we plug in 1 for x, negative 1 for y, which, by the way, like this could have been a very much like the initial step to like literally write down how, like, hey, well, let's move dx to the other side, and then we're integrating both sides to get, a y over here, y, you know what I'm saying? Like we could have maybe even like should have written that down. I don't know, like this whole time, you know, it's a y, right, over here on the left side. But we end up with c equals -3/4. I do declare. And so our final answer is y equals x squared over 2 natural log of x from over here minus x squared over 4 minus 3/4. Okay, moving on. Pause the video if you still need to copy that down. And we have one more juicy example. Okay, and it looks like this. Evaluate the integral of e to the x cosine of x. So when you're looking at this thinking, what am I going to let u equal so that it becomes simpler? When I take the derivative, well, you're looking at like kind of both of your options going, I don't really see a good option that kind of follows that strategy, but oh well, let's give it a try and see what happens. So let's do this. Let's let u equal e to the x and dv equal cosine x dx. So du will just be e to the x dx. V will end up being sine of x. And when we do the integration by parts formula, uv minus the integral of v du. Okay, this is our new integral. Is that any more doable? And I mean, you have to admit, like, no, it's not. It's not a more doable integral at all. So what do we do? Well, let's try doing integration by parts again. And I mean, it's hard to feel optimistic at this point in time, but like, okay, so let's just, if at first you don't succeed, so u equals e to the x, and that means for this integral, dv would equal sine of x. And so there's our du with the derivative. What is the integral, because we're taking the integral of both sides here technically, what's the integral of dv? V. What's the integral of sine of x with respect to x? Negative. Okay, what's gonna happen here? So remember, this is already locked in. Like, we already had this, you know, and we're basically doing a whole new integration by parts, you know, just for this. Okay, so minus, and then we have in parentheses, giant parentheses here, uv minus the integral of v du. Man. Well, again, is this integral? I mean, we're going to clean this up here in a second. Giving you a few more seconds to write this down, I suppose. But, I mean, think about even after we clean this up a little bit, like distribute the negative and basically clean up all these negatives and clear the parentheses. Is this integral now like any more? No. It's not any more doable at all. So what the heck do we do? Well, this is it cleaned up a little bit, you know, with distributing the negative and stuff. So like, you know, distributing the negative, that just becomes positive e to the x cosine of x. These two negatives here make a positive, but with this negative, the final sign over here is, so it's like, what the heck? What do I do? And do you even notice, please notice this, at least once I say it, not only is this integral like not any more doable, this is the exact same integral we started with. So it's like, oh my gosh, did we do all of this work, 2 rounds of integration by parts, for nothing? Like, did we do all this for nothing? Actually, ladies and gentlemen, it was all worth it, because you're not going to look at getting the exact same integral we started with. Don't look at that as a bad thing. look at that as a good thing, and we're going to use that to our advantage. Remember, the original problem was this, integral of e to the x cosine of x dx, which has basically been over here on the left side of the formula this whole time, technically. And so you know what we're going to do? Since we have the exact same integral here and here, check this out. This is going to be brilliant. We're going to move this to the other side. And since these are technically like terms, we're going to get this. And at this point in time, we have to do this eventually anyway. Let's toss in a plus c. Look at this. So now we have like 2 integral ex, e to the x cosine of x dx. So what do you think is the last thing we're going to do? We're going to divide both sides by 2 and basically have this solved for, our original problem. And so here's the final answer. You know, technically this c value is not the same as this c value, whatever, because, you know, when you divide a constant by 2, you're just getting like a constant. So, ooh, boom. Okay, now that looks better. And that's the final example. Like, that's as juicy as it kind of gets. You know, so quick recap, you know, examples like this where you could just do the like integration by parts formula once and it was over with. But an example like this where you needed like 2 rounds of integration by parts. Natural log examples where you kind of go against the norm with like what you let u equal and what you let dv equal, and like again what you're taking the derivative of and what you're taking the integral of when you're doing the formula. And then these kind where you basically do integration by parts twice, wind up with exact, like the wind up in an integral like the exact same one you started with, but then you actually, you know, just use that to your advantage and do this little trick and get this final answer. And that does it.